in the last 67 years, over 9 billion tons of plastic has been produced. It takes 10 to 100 years to decompose, at best. Some plastics will not decompose for 450 to 1,000 years after production. Plastic has become a global problem, finding its way to the tallest mountains and to the deepest depths of the ocean. In a 2015 report, the EPA released data saying landfills received 137.7 million tons of municipal solid waste. In the United States annually, 18.9% was plastic, second only to food. 3. Let's bring our attention to the measured number 137.7 million tons from the EPA report. There is a lot of information in the measured number 137.7 million tons if you know what to look for and how to read it. The first thing you may have noticed is the number stops at 137.7. Why would they stop at 137.7 million tons? Let's go even farther. Why wouldn't they report a more defined number like 137,786,354 tons? They didn't report a number that defined because they could not account for a number that precise. 4. The point of a measurement is to quantify what is actually there and communicate the quantities found. This brings with it inherent questions. Measurements of any physical quantity will never be 100% correct, and all devices have limitations. Measured numbers are treated in a special way to account for these limitations. To help clarify and recognize what is going on, measured numbers have some guidelines that consider estimation and certainty, uncertainty, precision, and accuracy, significant digits and non-significant digits. A measured number has information embedded within the number itself that communicates these limitations. The information found in the number include the following: 1. Certainty, 2. Estimation, 3. Uncertainty, 4. Precision. Guidelines and the embedded information of reported measurements thoroughly. Let's start out with what is certain and what is an estimation. An important step in a measurement is to clearly distinguish what we know to be true and what is a good guess. Certainty and estimation. Imagine what it would be like if we didn't have a way to define what is certain and what is estimated. Outside of counting, can you imagine what a mess it would be to guess how many people are in this photo? What if we raised the stakes where a business decision had to be made that depended on that number, like how much money there should be from ticket sales? One person may say one thing, and another person may say something totally different, and there is really no way to know for sure. Would the measurement change if it was the person paying the money from a person collecting the money? Imagine what the conflict would be if we would just go slapping numbers on things with no certainty. What if someone was just like, I am thinking there is 10 million people there, so pay accordingly? Is there 5,000, 500,000, 1 million, 10 million? Hell, who knows, but I do know it sure would leave a lot of room for someone to slip out of reality and someone else to make a biased opinion they could benefit from. Certainty and estimation are important. We need to know what is certain. We need to know what is estimated. We need to know how much to estimate. We need some way to clarify and define what is certain and what is estimated. Certainty and estimation are extremely important with measurements in science. Let's start out with how certainty and estimation is embedded in the number. In every measured number, there is a syntax or convention of how measurements are reported that tell you what is certain and what is an estimation. By convention, the last number reported as an estimation and the numbers before that are what we are sure about in the measurement. When we say we are sure about a measured number, we use the term certain, so in the number 137.7, the number 137 is certain, and 0.7 is an estimation. Looking at this slide, when a number is reported as 137.7, it really means 137.7 plus or minus 0.1, denoted as this symbol here. We estimate 1 unit of the smallest unit reported are the last number plus 1 unit or minus 1 unit, so the actual measurement could be 137.6, 137.7, or 137.8, all of which would be acceptable guesses. Examples. These distinctions can be found on the measuring device itself and in the reported number. Looking at this slide, we have one digit. Looking at this arbitrary ruler, we can see defined marks where it is certain 1, 2, and 3. We could report a length past these marks as certain. If the object was past 2 and before 3, we would report 2 with certainty and estimate one more number by dividing the space between 2 and 3 into 10 equal parts and imagining what number the object ends at. Mentally dividing by 10 can clarify and communicate conceptual meaning in a quick and dirty way. Looking at the red arrow, it is past the 2 mark, so we are certain it is 2. We can then imagine 10 equal parts between the 2 and 3 and estimate the position to be around 4. So, we report to what we know to be certain in the calibrated and defined marks, and estimate what is in between marks of certainty denoted in the last reported digit. T should be made clear what is certain, and values that are certain can give you peace of mind, but a measurement could almost be misleading if we recorded measurements that were so rigid we would not step outside the bounds of certainty where useful information is not recognized because it is not technically certain. Let's look at this slide. We are only certain of the 2. However, if we did not estimate, it would be a bit of a misleading measurement to only record what is certain, so 2.9 is a reasonable measurement. This is why measured numbers should be reported to the number of digits that reflect the precision of the measurement and/or the measuring device where both certainty and estimation are recognized.